Swayam Prabha. Digital India. Educated India.
So if there is no question, let us thank the speaker. Thank you so much.
Thank you.
So let us start with the second session of advances in optimization, and the first speaker is PSC Beacon presenter, Professor Christos Mervelias. Is he online? Professor Mervelias, are you there? Can you hear me?
Yes, I can hear you. I'm sharing the screen. Can you see it? And can you hear me?
Yes, we can see your screen as well as we can hear you. So Professor Mervelias need no introduction, at least to PSC community, but just for a sake of introduction, I am introducing him. Professor Mervelias joined Department of Chemical and Biological Engineering at Princeton University as an Anderson Family Professor in Energy and Environment in 2020. He has been working in several areas, like prominently he's working in the area of mathematical programming, sustainability, energy scheduling, and many more. He got several awards also, so I will not go in the list. He has served the leadership position at the Great Lakes Bioenergy Research Center and the CAST division of the AICHE. He is also a chair of several conference organizations, etc. Without delay, I would request Professor Mervelias to go ahead with his presentation. Thank you. Over to you, Professor Mervelias.
Okay, thank you very much. And thank you for the kind introduction. And also thank to the organizers, and especially Professor Srinivasas for the invitation to present this keynote talk. I was asked to talk about supply chain with an emphasis to future research direction. So what I have done in this talk is try to outline some problems or that we have been thinking about, outline some open questions and some future research directions, while also showing some results. So I'll start with two slides that I presented almost 10 years ago when I gave a talk at FOCAPO, and it was about supply chain optimization. So here is the definition of a supply chain: is a network that has different manufacturing options, transportation options, and the goal is to really convert raw materials to valuable products and deliver them these valuable products to the customers in an efficient manner. And in this kind of sketch, we show that traditionally process systems engineering has primarily been concerned with the design, optimization, and control of this manufacturing layer. But changes that happened in, I would say, maybe in the 90s, primarily in the 90s and early 2000s, led to the consideration of a broader set of problems. And the reason is that due to product customization and diversification in the chemical sector, we had to build what we call now multi-product facilities. Basically, we would like to still have big facilities to exploit economies of scale, but now the products that we want to produce are low volume. So what we do, we still go for big assets, but then we have to efficiently utilize them by producing multiple products. And that leads to a number of problems that I will be discussing in the next slide. So really process systems engineering, from addressing problems in this yellow layer, started addressing problems in all the layers. And when we say problems, really the goal of these problems is to coordinate and optimize the flows in this network. How do we do that? Well, there is a number of areas that we can look into, and a number of different problems. And these problems have been traditionally being classified in terms of business functions. So the four functions are procurement, production, distribution, and sales, and then time scale. In the long term, or what we call strategic planning, we just want to make decisions over multiple years, and the time granularity is maybe months or years. In the master planning level or the medium term or tactical planning, we're considering horizons of months or years, and our decisions are in a granularity of weeks or days. And then in the short term or operational planning, we want to be making decisions on an hourly or daily basis, and our horizons are weeks or months. And the next kind of step in the evolution of the problems that process systems engineers have been addressing was the integration of some of these problems. And one famous, let's say, integration is the integration of planning and scheduling. A lot of work has been done in this space. I'm not going to go through a lot of the details. Maybe I will say is that while there are many different ways to integrate these problems, the focus, and rightfully so, of the PSC community has been on the integration in the production column or the production function. The reason being that production is sector specific, right? One could argue that in terms of demand planning, every sector has some demand planning. Yes, they are a little bit different from each other, but the methods that have been developed in operations research are almost readily applicable in chemical engineering, whereas the production column is different per sector. So it can be quite different actually from discrete manufacturing. Now, a lot of attention has also gone into the integration of scheduling and control, but I would say control is somewhat outside the scope of supply chain. So control, if you can see the laser pointer would lie here in terms of time scale, and there has been also a lot of work in that space. Now, just to give a couple of examples of horizontal integration, I'll use here, examples from my work, but there are also a few others. So in an example of horizontal integration, here we are trying to think how multiple functions will work with each other. And in some cases, these different functions actually are problems of different entities. So here is an example where industrial gases supply oxygen to steel manufacturers, to completely different decision makers. And both of these entities interact with the utilities because utilities provide electricity. And both air separation and steel manufacturing require a lot of electricity. So the questions there are a little bit different. It's not necessarily that the scale of the problem is very big, but we start thinking about multi-agent, collaborative decision-making and planning, so other sorts of problems. And this problem can even be extended to consider one more entity, a refinery, which also provides materials both to a chemicals manufacturing facility and industrial gases, and vice versa. All of them interact with power utilities. How do we solve this problem? So there can be the challenges, and therefore the methods that have been developed in the field can be both computational and algorithmic to solve these large-scale problems, but also thinking about frameworks. Okay, so let me now move to supply chains as an example of these problems. Biofuel supply chain as an application area. And I will be using biofuels as my example in this talk, but as I will discuss the types of questions and problems that I will be trying to describe are common also in other areas. So in a typical supply chain, and I would say in the majority of the works that have appeared in the past, we are given these 4 bullet points, right? So we are given the raw materials and the final products. There isn't so much flexibility in terms of the raw materials that we can use. The location and the availability of the raw materials is usually known, and it doesn't change necessarily over time. There is relatively constant material quality. And then finally, the nodes in the supply chain are known. Even when they are not known, we choose from a known set of nodes. So the problems in supply chain for biofuels now are very different, one could argue, because all of these assumptions do not hold. So we have many different feedstocks, many different bioenergy crops can be used to produce the same product. It is highly distributed geographically, which means now that the typical trade-off of capital that we want to make capital investments bigger to have economies of scale do not necessarily hold in this case, because as we make a biorefinery bigger, that means that the feedstock cost on average will increase because we have to source it from further away. It's not clear which lands we should be using. I will be coming back to this point. It has been suggested that we should be using what is called marginal lands. These are lands that are currently not used for food, so we avoid the food versus fuel competition. The quality of the feedstock changes very much. It changes with time, but also changes depending on the decisions we make in terms, for example, of irrigation and fertilization. And as I said, this is not an issue, this highly distributed geographical nature of the resource, of the main resource. It's common also when we're thinking about solar systems, wind systems, and so on and so forth. So the challenges that I will be describing are in some ways common in all these types of systems. Of course, a lot of work has been carried out in the field in this space. I won't have time to describe the contributions, and these are just some of the groups and key papers that have been published. I won't have time to go through all of them, but what I would like to argue is that in all of these actually works, it has been assumed that the decisions regarding the lands that we will use and the type of crop and the management of the crops is given. It's a parameter. And here, this paper is actually from our group, so we have also relied on this assumption, which is not necessarily the case. Actually, these systems have not been established. It is not clear what lands we should be using, and there are many different definitions of these marginal lands. And we are not at the stage where we want to design. So we want to develop these models not to make decisions, but to understand. And in order to understand, we have to consider all the different options in terms of the different types of lands that are available, which ones we should be using. Once we make these decisions, which crops we should be using, how we should manage it. So, and to understand the systems, we really have to account for the spatially explicit trade-offs that are present. So I'll start with these 2 points that I made about lands and crops. So first decision, which are the lands that we should be using? This is not an easy question because there are many, many different types and definitions of marginal lands. In this figure, I'm showing just some of them. For example, abandoned croplands is a land that can be used. Formerly irrigated lands are lands that can be used. Which one of the two? And the Venn diagram, there is significant overlap in the Venn diagram. An additional, challenge is that what is today classified as marginal land, it may not be marginal tomorrow. And here it's climate change that really changes completely these definitions. So, and I'll give 2 examples. Lands that in areas which are currently very wet, this can change because of climate change, and the other way. Areas that are too dry or too hot can become more easier. They may not become prime lands to be used for food, but they can be used for biocrops. So here, for example, too cold. I spent many years in the University of Wisconsin. It has been actually now established that crops that wouldn't grow in Wisconsin 30, 40 years ago, they can now be grown because the weather is becoming warmer. This is one of the few cases that, the only one I know, where climate change might have a good outcome. And then this graph shows that even if we had perfect definitions of what is marginal land or what is an appropriate land, it would still be difficult to decide which is the best crop to cultivate and even whether it should be used for food or energy. So in this graph, the x-axis is, let's say, a metric about land quality. When the quality is high, we know that the best outcome, let's say, or the term here is the ecosystem services that we obtain from that land is to be used for food. then as the quality of the land decreases, the best use would be to be used for energy. And then if the quality is very, very low, then we cannot do anything really with these types of lands. But determining these thresholds is not trivial and is going to depend on space. So how do we address that? Well, this is, where expertise from other domains is necessary. And one of the main points that I would like to kind of maybe drive in this talk is that to address these new systems, we need collaboration. We need to collaborate with experts from other fields, or really learn learn about these other fields and do the work ourselves. But really, we would have to invest the time and effort. So in the area, people in geography and agronomy, they use drones to get images of these lands. They train these images. So for certain lands, for a training set, they know where is the land, whether it's, let's say, it has been used as a cropland or not in the past, and for what types of crops. They train these machine learning actually methods, and then we use these methods. They apply them now to just images without the information, but now they can come up with some probabilities regarding the quality of the land. So they go through this exercise, through this training, and then they have these tools. Now, what makes it a little bit complicated to develop these tools is that there are multiple definitions of marginal lands. These are all different definitions for marginal lands. So we could potentially use all of the areas identified under any of these definitions for bioenergy. This is an image of historically abandoned lands as identified by the tools that I just described earlier. And this would be the detail and the images over multiple years. In this graph or in this sketch is the same, the lands that have been identified as formerly irrigated by these types of tools. This is the imagery that it has been used, and you can see that there are many different patterns depending on the systems that are used for irrigation. So there are photos of these systems for some years, and then the machine learning algorithms would determine, and this is the figure here showing the US map, shows which lands have been identified as formerly irrigated. That's a lot of work to do it for an entire, for a big country using very different definitions, but it has been done. So this is a tool, actually you can check it online. It's a tool where you can pick the definition that one would like to use. You can then pick even how many years are required for the land to be abandoned to be classified as former abandoned land. And then you get that map. You see here the pixels are a very low resolution. You get the information as to what lands can be used. Okay, so the data are there. The tools have been developed, although there is continuing work in this space to develop these tools. Then we have to be able to predict what are the yields. And again, as I said earlier, this is probably an area where it has been assumed that we always know the yield of the biomass. Interestingly, again, so that's an area that maybe chemical engineers have not worked extensively, but interestingly, the models that are used for these predictions, actually people call them process models, because in a way, and I'm showing here this graph here, can be viewed as CSTRs connected, and these CSTRs have different residence times and different flows. So how carbon is going to reach the ground and then be used by the plants to grow, and some of this carbon is going to be sequestered in the ground, is actually, you can see here, we have reactions, we have CSTRs, so it's actually very interesting that chemical engineering principles can be used and are used in this type of models to predict not only the yield of these crops, but also other environmental outcomes. What happens with nitrogen, fertilization, what happens with water, how much water is needed, how much carbon is sequestered in the ground. This is a schematic of the different parts of these models, and I don't have the time to go through it, and also I don't know all the details. The other point I would like to make is, again, some interesting kind of analogies. There are many different models that have been proposed in the literature to predict, to make these predictions. People have started to think about constructing machine learning models for prediction. So using these models, these detailed systems models, to make predictions, do experiments in very limited areas to try to understand how the weather, for example, affects these outcomes, and then using weather data in a much bigger regions, predict the yield without actually doing the experiments. And the field has progressed quite a bit there. People have started to think about ensemble of machine learning models and so on and so forth. This paper comes from a group in Michigan State University where they have done a lot of work in this space. Okay, so this is kind of, again, I wanted to give an idea of the types of results that can be obtained. Again, this is not our work. Is again from the same group in Michigan State University. The result of all these models, again, two-step process, detailed system process models where you have these CSTRs, what we would call CSTRs. They are used, verified with experimental data. Then these models, either as they are or the machine learning surrogate models built from them, are used to make predictions in entire regions. So this is the US Midwest. These are the predicted yields using these models. So you can see here the color illustrates what's the yield if a land has been already identified as a bioenergy land. And not only that, using now different weather data from different years, we can get some histograms about the probability of having certain yield. So, and then this is without any what is called land management. People have also developed models, predictive models, which would tell us, again, the yield, the soil sequestration, all these key outcomes as a function of, for example, fertilization. And what is shown here in this, on the left, in these 4 panels, is predictions of 4 different process models, upstream, descent. So this is epic, salus are different process models. And this is the ensemble, the prediction from the ensemble of the models. Okay, so finally to a problem that we are more familiar with. So we need to make land decisions, crop decisions, and biorefinery decisions, both location and technology. And so in the technology aspect of it is what I would say we have, we're very familiar with. It can be formulated as a superstructure optimization problem. This is the superstructure of the technologies that have been studied in the center that I am a member, that our group is a member of, the Great Lakes Bioenergy Research Center. So as we can see, different pretreatment technology, different hydrolysis technologies. So nothing, very new here. What is interesting though, and somewhat new, is that it's not just, sometimes we have to also be thinking not just for a given product. For example, what if we would like to produce butanol instead of ethanol? As a design problem or a process design problem is solved, but we should also be thinking the properties of butanol, that they are slightly, they are a little bit better than ethanol. So how do we kind of do an oranges to oranges comparison? Is not that straightforward. In most existing biorefinery designs, the lignin, and I'm thinking now about biorefineries based not necessarily on cellulosic crops, the residue streams are converted into heat and then electricity to meet biorefinery heat and electricity demands, but then also the excess electricity is being sold to the grid. This is not necessarily the case. A lot of research has been happening. There are Gordon conferences on lignin valorization. So this difficult to process polymeric compound could potentially be also converted to fuels or chemicals. So what are the trade-offs? Same thing for other residue streams. So again, many interesting problems, but today I will be focusing more on the supply chain aspect of the biofuel supply chain. So this is kind of now the big picture, I would say. Actually, this is a slide taken again from this center that I am a member of. We have, if we want to consider the entire system, in some ways we have to have a good understanding of our plant and landscape systems. what we do in this space would generate parameters that then can be used in the integrated supply chain model. We have, again, considerations coming from the biorefinery, what's the best design, what are the best products, what are the technologies, what's the right size and location. All of these are going to generate parameters that then would be used to formulate these larger models. Again, I think the key point that I have to make here is to understand these systems. We are not at the stage where we can design. There is no single decision maker for these systems, but just to understand. So this has been done, and I'll go now a little bit more into the optimization for some small systems. And that's, I think, very, very important. There are still many, many open questions for bigger systems, regional systems. So from these simulators, system simulators for crops, at the end, a lot of inputs. I have described some of the inputs that are required. At the end, this part is going to generate crop data. What are the yields in different types of lands? What are the other environmental impacts? I haven't spent a lot of time for the generation of the spatial data because this is a problem that is common also in let's say, older problems, right? So what's the transportation network? Where are the potential locations for the biorefineries and the depots? Depots are facilities that they do some processing, so the feedstock is densified, so then shipping it over larger distances is not so expensive and energy intensive. So we have to decide where are the potential depots. These are real maps for the state of Wisconsin. And then finally, we have the inputs for the biorefinery. We have to put everything together and come up, with a solution. The solution would look something like this. We would obtain simultaneously the locations of the depots and the biorefinery. So here you can see these small black dots are the depots. They are installed farther away from the biorefinery. So so here we have densification of biomass and then shipping to one central biorefinery. That's in the state of Wisconsin. And these are the decisions that we have to make. Now, just again to give a flavor of the model that is being used, again, these are very large scale models. This is the objective function. It has to be formulated as a stochastic program because the yields and other environmental outcomes in the lands can be very, very different over the years. So there is a capital kind of set of decisions. These in the stochastic programming jargon as first stage decisions, so we have to make them for the next 20 or 30 years. But now the evaluation of the operation of this system is done as a second stage decision. So we have here, for example, the key variables. So the feedstock cost is scenario specific, production costs are scenario specific, and so on and so forth. The data for this come from these simulations of these tools that predict environmental outcomes. So in terms of capital decision, we have to select which technologies are being installed at the biorefineries. Once we select the technology, we have to decide capacity and then cost it. In terms of feedstock decisions, this is the part that it becomes spatially explicit. So it's very, very large scale. It's very difficult to solve this problem. So we have to make some approximations. I'll be happy to discuss at the end of the presentation or offline the types of approximations and surrogate models that have been developed for this spatial explicit aspect of the supply chain. But at the end, we want to be able to have a model that will tell us how much we can take from a specific pixel in the supply chain and what is going to be the soil sequestration there, what is going to be the fertilization and irrigation that is needed to obtain this yield. And then again, to give another example of the terms here, the environmental impact, again, is going to be scenario specific, is going to change over time, and it has greenhouse gas emissions from transportation, from production, for harvesting, production in the biorefinery, harvesting, and so on and so forth. So let me just maybe show some, what really these spatially explicit approaches mean on a map. Probably you have noticed that these maps are very small still. So the previous map was for the state of Wisconsin. This map is for the state of Michigan. The two state schools in these two states are actually the primary institutions in the Great Lakes Bioenergy Research Center. So that's why we have very rich data for these two states. So this would be the grid. So the black dots in this map in the state of Michigan, what is white here outside, this one is, this is lakes, this is lake, and then this is another state. Black means land that can be used, but we cannot be at this level of detail. So we are using different grids. So from 625 square kilometers down to 16 square kilometers, these are the grids that will be generated. And even if we go down to the 16 kilometer resolution, a pixel here, really only a small fraction in that pixel has marginal land. So for every pixel, we identify the fields, but then we say, okay, these fields are going to be approximated based on their location within that pixel by a single point. And we do that for all the pixels. And this would be the results now that we would obtain if we run these models at different granularity. At the county level, that's what would be the supply chain. One biorefinery located in the center of the state and few depots, no irrigation. The color of the land that is being selected indicates whether we irrigate or not. My apologies. Here we have to irrigate everything. As we become more, the granularity increases, we start now getting more information. We pick some fields that maybe do not need irrigation. So you can see from the county level, now we start having some different decisions, definitely fewer depots. And then at the end, when we have very granular decisions, we have very few depots. Now, why is this important? This is the emissions of the systems that are being designed using different granularity, and we can see that the production emissions in the biorefinery and the transportation decisions do not change very much. But the benefit from salt sequestration increases significantly as the granularity increases. So it is important actually or we could design better systems if we do this analysis with these spatial explicit models. Going forward, impact of uncertainty. This is the object, we are minimizing cost. This is the objective function value. If we are using the expected solution, evaluated at different years, and we can see that the cost can be significantly higher in years where the weather was really different, is significantly higher than the solution that we would obtain using stochastic programming. This is the recourse problem, the green, and we can see that in many years we can do significantly better. The challenge, unfortunately, or fortunately, because we have problems to look at, is that as we increase granularity of our grid and number of scenarios, these problems become intractable. So this is, I'll focus on the right pane here. This is the solution time as we increase granularity from left to right, from the county level to 16 square kilometers cells. And at the same time, the color of the bars indicates the number of scenarios. We increase the number of scenarios. So we cannot solve these problems. I see I'm running out of time, so maybe I'll skip the part about carbon capture and I'll go directly to some preliminary results. This is, again, same solutions only for the state of Michigan. If we also add into the system the capture, what we do with capturing CO2, not in the land, but now at the biorefinery. And these are two solutions using two different parameters, sets of parameters for social cost of carbon and sequestration credit. But let me now finish with some kind of open questions. 2 slides and then I'll go to conclusion. So what I have shown is at a state level. We have to do that at a regional scale. If we really want to understand the systems and answer the question, are these systems beneficial environmentally, we would really have to solve the same system at a much, much bigger scale, which brings lots of computational challenges. It's not only liquid fuels that can be produced. One could argue that we can produce electricity or hydrogen from biomass. Answering this question, whether it's better to produce electricity or not, now brings some other considerations into the picture. The electricity grid
in a big region can be very different, both from a price standpoint and an electricity mix. The mitigation potential can be very different if we are replacing dirty electricity versus cleaner electricity. If we're thinking about sequestration, we cannot simply assume that the CO2 in the biorefinery is captured and sequestered at the biorefinery. We should be thinking, where are the caverns that can be used for sequestration? So that will bring me to my conclusions. As I said at the beginning, the PSC community has made important contributions to the supply chain, especially in the production, let's say, function, the business function. But studying these new types of systems requires the development of new types of approaches and models. So, and this, I'm talking here about renewable energy systems in general. These are some of, I think, my takeaway messages is that we have to be having real data or realistic data, because the insights that we would obtain can be very different if the data change. The goal, again, is not so much decision-making, but it's identifying the major drivers and trade-offs for these systems. We have to collaborate with other experts. I think we cannot avoid that, and really learn in some ways their disciplines a little bit. And we have to be expanding the boundary and considering new aspects to it. But once we have done all of the above, the models that are going to still have all the challenges that we are, I think, very comfortable addressing. So we may have to use different submodels, so there can be surrogates. We have a lot of uncertainty in these systems. The models that will be generated will be large scale and will be requiring new solution models. So with that, thank you very much for your attention, and I'll be happy to take any questions.
Thank you so much, Professor Marvelius. Thank you for merging sustainability, supply chain, machine learning, bioenergy, all are merged. So this is time now for the question answers. So is there any questions to Professor Marvelius?
Hi, Christophe, François Maréchal. I have a question concerning the multi-scale dimension of the supply chain. So typically you have a first collection zone, and then afterwards you will distribute over bigger places. So and then it results into a very, very big problem in terms of mixed integer linear programming also. So can you comment a little bit on those aspects of perhaps model size reduction and approximations that could be used there?
Yeah. Thanks, François, for the question. Yeah, so this is a very, very big challenge. So what we have chosen to do, I'm not saying that this is the only way, to try to address it, is we don't have integer decisions at the pixel level. So we try to have a linear approximation. So the approximation is really the cost increases for establishing and harvesting as a function of the amount that we harvest from a given pixel of the map linearly, although it doesn't go through zero. So we have an approximation of the decisions that we have to make for crop establishment, harvesting, and irrigation. It's an approximation, but again, when we have thousands of these points, we couldn't afford to have binary variables and also stochastic programming. If it was deterministic, if we could assume that the yield of a pixel would be the same every year, we could have binary decisions, and that would allow us to have a little bit more detail in terms of what happens at that yield. But what we have tried, stochastic, we cannot do it. So it's an approximation. And that's an open question, actually. I think that's, if people can come up with methods to address these problems at the 16 square kilometer region, regionally, scale regionally, that would be great. But it's an open question.
Hi, this is Yogendra from IIT Bombay. So actually, I have a non-technical question. So we have also been doing something similar in the Indian context. And the question now is, what next? So these biorefineries don't exist, and hopefully these models will be used eventually for decision making. So I just want to know your thoughts. Have you had any success in making maybe DOE or USDA take note and actually use these models?
Yeah, thanks for the question. Very, very good question. And maybe I will add to it that even, we develop the technologies and then the farmers are not willing to make the changes that are required. So I think we are just at the, so DOE, I think, is listening, but we are still at the stage of understanding even what would be good crop or what would be appropriate lands, how we would rotate the crops. I think there is still a lot to be understood about this system. So, to answer the question, I think we haven't had any success with DOE. I think DOE is listening and they want to understand more before potentially offering more incentives. I think there are other aspects, ecosystem services, right? Many people worry that if we have these monocultures over big areas, that would have very negative outcomes in terms of ecosystem services. So how do we maybe have polycultures, have strips of land with this type of crop and another strip of land with a different type of crop? All these questions are still open.
So is there any question to Professor Mervilias? So I have one question, Professor Mervilias. I'm Manoj Ramteke from IIT Delhi. So in your optimization formulation, you have included the capital cost, you included land cost, environmental cost. Why not social cost?
Yeah, so one, it was the monetized impact or social cost from.
So for instance, if you are changing the crop from one crop to another, there is a social impact involved in that. Maybe for a bigger farmer, it is not, but for a medium and lower.
Absolutely. That's a good point. It's very difficult to quantify. But if you remember, actually in one of my slides, we had a social cost of carbon.
Okay.
In one of my slides, when I was saying case 1 and 2, that was one of the parameters. But it was just sensitivity analysis because I don't think good point. Very good point taken. And goes back to the point about the farmers and their unwillingness to change, and there is a social cost. Now, maybe the point I would make is that we don't go from food to bioenergy crop. In all these analyses, all the lands were what we call marginal lands. So there was no food versus land competition, but still there is a landscape change cost. Thanks for the question.
So thank you so much. So let us thank Professor Mervilias once again.
Thanks again for the invitation, for the kind invitation. And I'm sorry I cannot be there.
We would have been, we would be happy to receive you here maybe next time.
Yeah.
Okay, thank you so much.
Thank you.